All right, if that changes, let me know, okay? All right, intro to structural engineering, guys. Structural engineering is one of the branches of civil engineering, and it's kind of, in the basic toolkit of every civil engineer. So, I'll go through the very basics. What is structural engineering? Engineering structures. I love it when you can use the words of the definition in the definition. Structures are all about, I should have thought this through earlier, you know. It's all about what forces do to things, buildings, structures, whatever the thing is. We want it to be there. We want it to resist the force, okay? So I'm gonna put a basic equation up here, which is R star must be less than or equal to phi R U naught. Okay, R is an action. Phi is a reduction factor, RU naught is a capacity. Okay, I'll talk about each of these in detail. When you design a structure to withstand a force, you need to make sure that the capacity of the structure is greater than the force, okay? That's a really dumb way of saying if the capacity is less than the force is gonna win, okay? That is the force side, that is the capacity side of the equation. The capacity must be greater than the force. Everyone good with that basic concept, okay? Whenever we have a force, we have what we call action. We have anything that's got the capacity which is the capacity to resist that particular action, okay? There's a bunch of different kinds of forces, so you'll see like F star is less than phi R, Fu naught. You might be M for moments, might be V for shear forces, whatever it is, whatever the action and the applicable capacity to resist the action, okay? The RU naught is our capacity. The U naught means the ultimate capacity of that thing, okay? So if we have a pole here like this and the force is pushing on it, the capacity, the RU naught is the capacity of this pen to withstand that force pushing it sideways. All good? Okay. So when we do structural engineering, we have to make sure that our capacity is greater than the force, okay? So that, like, I've hopefully emphasized that enough. We're all good with that. The asterisk means ultimate force or ultimate action, okay? We talk about actions, we talk about ultimate actions. It's not just the throwaway word. What it means is that we exaggerate the force or the action and we underestimate the capacity, okay? Because you think about, you might have heard the term safety, factor of safety, okay? If you build something that's twice as strong as it needs to be, it's got a safety factor of 2, okay? That means the capacity is twice as much as the force. What we do in structural engineering, especially in limit states design, it's worth writing that down. Limit states design is we exaggerate the force, and then we call it an ultimate force, and we underestimate the capacity, and we call that the RU naught, just the structural capacity of something, okay? And when you overestimate the force, you underestimate that condition is always satisfied. Because if that condition is not satisfied, the thing breaks or falls over, does whatever it is, okay? The phi factor is what we call capacity reduction factor. And that varies according to the situation and the materials you're using and what you're actually designing. So, for example, if we are designing a concrete beam, it's a bad example, if we are designing a steel beam, the phi factor is almost always 0.9, okay? That's a reflection of the fact that steel is a pretty good material. It's got good consistency, we know what it's about. We can assume that it's going to be 90% as strong as it is advertised, all right? Timber varies from 0.9 down to about 0.7. Concrete varies from about 0.8 to 0.6, depending on, the situation. And the reason that concrete is less is because concrete is, it's a less homogeneous material than steel. You know less about it. It's subject to all sorts of changes when you're making it, when you're casting it, all that natural variation. Now the 5 factor I said for timber, there's more that goes into timber here, which gives us more conservatism. But that's basically what's happening there. All right. Any questions on that so far? Okay. Please interrupt me with questions whenever they come to you. Okay. It's a small class. We can run it like a discussion. No problem there. Limit states design. You might come across a term, working stress. You might come across the term limit states design. Basically, it's 2 different ways to get to that. We have what we call limit states design, so there are several limiting states. One of the limiting states is strength. You have to make sure what we're designing is strong enough, okay? That's probably the easiest and most straightforward one. You understand what strength is. If it's not strong enough, it breaks, okay? That includes things like collapse, you know, the failure that can kill you. Another second limit is called, a common one is called serviceability, okay? Serviceability is about the ability of the structure or thing to do what it's supposed to do, all right? So for example, if we have a beam and we put a load on it, it will bend a lot and not break, but if it bends too much, it can't really do what it's supposed to do. If we take this building, for example, the strength is about whether this thing's going to collapse or not. That's easy. The serviceability is if that beam bent so much that the snow actually sat on the roof and didn't drain off and the water came in the building, that would be a serviceability failure. If something moves so much that the doors jam and the windows break, even if it's strong enough that it's going to hold you up, that it's going to support the house, that's a serviceability failure, okay? So sometimes things will fail in serviceability before they fail in strength. Sometimes things will fail in strength first. If something fails in strength, it will automatically fail serviceability. Okay, that's kind of obvious. If it's fallen over, it's no longer serviceable anyway. All right, does that make sense? Okay, so let's look at the load side of the equation. And here we have turned to Australian standards. This is a fairly old book. And this is just a collection of 5 or 6 Australian standards. And the one we refer to here is called AS 1170. All the Australian standards start off AS for Australian standard. Sometimes they start off AS/NZS because we do a lot of this in partnership with New Zealand. Okay? The Euro codes, similar idea, different set of numbers, different set, the way they're authored is different. Okay? So 1170 is a set of loads called the loading code. And there's 1170.0, which is all about structures and loads and how you design. 1170.1 is all about your dead loads, your live loads, and the kind of actions that happen. 1170.2 is this one. It's called wind actions. 1170.3 is earthquake, 1170.4 is snow loads, 1170.5 is I've forgotten what it is. Okay? So 1170 covers basically all the loads on structures. That's what it's all about. When you come to design a structure then, if you want to design a steel structure, you have to look up the steel code, which is AS 4100, 4100. If you want to design a timber structure, you're going to be in 1720. Okay? You'll get to know these numbers, or you can Google Australian code, AS wind codes, or timber code, that kind of thing. There's a lot of them that you'll get very familiar with. 3600 is a favorite for engineers because that's the concrete structures code. Okay, and a lot of these codes then refer to each other, that kind of thing. Since we're talking about codes, they always come with a date. This is AS NZS 1170.2 2011. That got updated in 2021. So this is the 2021 version of the wind code. And these 2 documents are quite similar, but there's a few different things. So they tweaked a few tables, they changed the methodology in a couple of things, they changed some of the factors. So look, if you design to an older code, you're almost always going to get it pretty correct. You might just find a few things that have tweaked and changed in the new code. Okay. When I wrote the static wind loads topic, that code was enforced, but I've annotated the topic to highlight the changes to that one. All right. So, first thing you do when you're designing then is you work out the loads on your structure. Okay. So let's take a theoretical structure. What structure do you want to look at?
Bridge.
A bridge. All right. Let's look at a pedestrian bridge. There's a bridge there. Let's make it a nice suspension bridge like that. Okay. And there is our happy engineer on the bridge. All right. Okay, let's consider the loads on the bridge deck. All right. So we're going to design that bit of deck. Yeah. We're going to design. Oh, if you look down on the deck, that deck will be like that, and it's going to have beams going across it like that, and it's going to have planks going that way. So we're going to isolate and design that particular beam. Okay. What are the loads, possible loads on that beam?
Weight of the person walking across it.
Beam loads. What was that? Person? Wait.
Weight of the person
Yep.
or people.
What else?